talking to you. This is work that I've been doing for a really long time now in collaboration with Jörn Randrup at Lawrence Berkeley National Lab. And we've been working together with the University of Michigan group for quite a few years now. Have several students work with us, and I'll turn on my video so you can see me. Hello. So I'm going to kind of put together a little bit of what was talked about at the beginning of the week by Kyle and by Nathan, and then go drill down a little bit more into the specifics of fragment angular momentum. Okay. So fission is a really complicated process that involves multiple scales and different forces. So what Kyle is talking about was just this left-hand part over here. And Nathan was discussing yesterday is the emission of neutrons and photons, and then the delayed processes. So fission is really interesting to study in terms of a physical process, because it involves 3 of the 4 fundamental forces of nature. They get weaker as you go along, and the timescales get longer also. So the fission and neutron emission is governed by the strong force. If you drill down into the nucleons, you'll find that there's quarks and gluons inside, but that's another lecture I could give another time. But the angular momentum is generated about here when the 2 fragments separate, and then as they're hot and excited after they separate, and they want to cool down, and the most efficient way of cooling down is to emit neutrons, because that carries away more energy than a photon does, simply because it also includes a separation energy. It costs some energy to release a neutron from a fission fragment. And then after that, when you can't emit neutrons anymore, then there's the electromagnetic force governing photon emission. And then you're down from fission fragments here to fission products. And or then later on you have talk about cumulative products when you've included the beta decay that's governed by the weak force. So this is on a much longer time scale. So strong force governs the neutron emission. That happens really fast. Electromagnetic force governs photon emission. The time scales are down here. So you can see you go from like femtoseconds during the fission process itself to microseconds and even longer for the cumulative yields. And there are specialized physics models that are required to really study complete fission events, and that takes a lot of phenomenology. And Jörn and I have been developing FREYA, which stands for Fission Reaction Event Yield Algorithm, and it's pronounced the Danish way, so FREYA, not Freya. That's the Swedish way. And this was the first fission model that was ever published and made generally available. And basically, everything that I described is governed by conservation of energy and momentum. And you can really go a long way with the conservation of energy and momentum. And it can explain a lot. It can't explain everything, because you need like nuclear tables for the nuclear masses. You need information about different levels for photon emission. There's all kinds of things that go into it, all kinds of nuclear data. So you can't just plunk it in and you don't need much to get started, but to do a good job, then you need more and more data. But FREYA is a fast code. It's fast enough for users to study fission with different isotopes and energies on a laptop a basic Fourier run of 1,000,000 events takes, 15 seconds or so. And there are other codes that are similar in concept that differ in the details, and I'm not going to go into those specifics here. But there's CGMF from Los Alamos, FIFRLAN in France, and GEF in Germany, and we all have slightly different approaches, but they're all based on Monte Carlo, and I'll explain why that's useful pretty soon. Other codes that exist are deterministic and based on average events and are tuned to subsets of average data, which means that they're probably pretty good for describing what happens in a reactor where everything is going on at once. But if you're actually doing a fission experiment, or say trying to detect some kind of material where you have a small sample, then you need something that's a little more specialized. And I mentioned Freya is pronounced the Danish way. Freya is one of the Nordic gods and goddesses. Here she is riding in her chariot pulled by cats. And people I'm a theorist, so we like to say that getting theorists to collaborate is like herding cats. So all these cats are pulling a chariot, so that's even better. Okay, so this event by event modeling that makes complete fission events every time is really efficient for studying framework fission. And event by event is something that's done a lot in, say, high energy physics, where there's also codes with cute names like Pythia, based on the Greek god who could tell you the future. So it's used a lot when there are multiple outcomes. So, what Carl was talking about on Tuesday, when you have these different ways of deforming the nucleus, and then there are many different ways that they can split. And then this gives you a distribution of fission fragments. It gives you a distribution of excitation energies, kinetic energies, and so on. And so, you can sample fission yield, sample fission total kinetic energy, and then do this very efficiently many times, and you can get a really good idea of what's happening in fission. So sorry, that's I don't know how to silence our local. I have not figured out how to stop the landline. I should have taken it out of here. I'm sorry. So this calculational framework is easily adaptable for studying fission, as I kind of just described. And we want to have a fast generation of large samples of complete fission events, which means a full kinematic information on all the final particles, basically the two product nuclei. After the neutrons are emitted, you have the fission products, which are different in mass number, but not in charge. If you have wait long enough and there are beta decays, then you also change the charge of the nucleus. Anyway, then you also have, say, anywhere from 2 to 4-ish neutrons for, say, spontaneous fission or thermal energy induced fission, or you can go up to higher numbers of neutrons, depending on the chance of the fission, which Nathan sort of alluded to yesterday. And then you have N photons, and there's an advantage of having samples of complete events. That means you can really extract any observable you want, and you can look at fluctuations and correlations. And what's really good if you're like trying to design an experiment is you can really use a code like this to say model your proposed detector and see if it's really going to measure what you think it's going to measure. And a code like Freya can be incorporated into transport codes as well. So why correlated? Because every part of a fission event is correlated. I mean, the deterministic codes are more like on the left-hand side here, where think of it, a fission event as average with a bunch of neutrons and photons just coming out. And like the MCMP code that's used a lot in Los Alamos, MCMP6, before a code like Freya was included, that the reaction would just emit a bunch of new photons, and then it would decide if it was an elastic scattering or fission or whatever, which is kind of like putting the cart before the horse, because then you have the neutrons out the door. I mean, the photons out the door before you even know what happened. So a discrete event by event fission model like Freya will follow every step of the reaction in detail, and so you have correlations automatically included. And another obvious consequence of having a deterministic code is that there's no conservation of energy or momentum. Okay, so I'm going to give you a very quick run through on how Freya works, to step through what happens in a fission event. So for a given nucleus that's going to fission, that has a certain charge Z and mass A, so it also has a neutron number that's A minus Z, and it has a certain energy. Excitation energy is 0 for spontaneous fission. That's a tunneling process. And with neutron-induced fission, you have the energy of the neutron that comes in, and then you talk about, say, E sub n is like the incident neutron energy. But you can also do, say, photo-induced fission or other types of induced fission. The thing that matters, because as Kyle discussed in terms of the compound nucleus, is that it doesn't really remember how it got to that excited state when it's fissioning. The point is that it has a certain excitation energy and it has a certain charge and mass, and then you can really go from there. So what Freya does with the compound nucleus is to select the charge and mass of each fragment, either from data or from a model. Kyle mentioned BROSA. That's one particular model where you can basically fit 5 Gaussians to the fragment distribution. There are also in Freya the possibility of using yields that were determined by a macroscopic method that he also mentioned. But you just choose the one fragment, and then the second fragment, mass and charge, is obtained by assuming binary fission, and from mass and charge conservation. And then you know both fragments, and you can calculate the fission Q value based on their charges and masses. And then that Q value is split between the total kinetic energy of the two fragments and the total excitation energy. And we take the total kinetic energy from data and sample from that distribution based on the mass of the heavy fragment, for example. And then what's left over then is the total excitation energy. And that's really divided between, I said the fragments were hot, they're also rotating. So there's the rotational energy of the fragment that's spinning around, and also its intrinsic excitation energy. And it's kind of separable, like Nathan mentioned yesterday, that typically the neutrons come off first, and then photons. When you get close to where you're getting close to the neutron separation energy, there's more competition, but typically there's not a lot before that. So we kind of deal with the intrinsic excitation energy first, because the spin temperature that sets the level of the rotational energy of the fragments, that's mainly dealing with photon emission. That's how the photons kind of get boiled off and slow down the spin of the fragment. So first we deal with the intrinsic excitation energy that gets divided between the fragments based on something called the level densities. And I think Kyle showed you a picture of some nuclear levels on Tuesday. And so there's a thermal fluctuations because the fragments are kind of small systems in that sense. So we use those thermal fluctuations to obtain the final excitation energy sharing. And then because those fluctuations change the energy slightly of the total excitation energy, we take away from the total kinetic energy to maintain kinetic energy conservation, which also is equivalent to making a width of the total kinetic energy distribution. And then we include spin fluctuations to conserve angular momentum. And I'm going to go into how that angular momentum is generated after this discussion. So we include some possibility of pre-fission neutron emission. This is not the same thing as fission neutrons. The pre-equilibrium emission basically means that the neutron comes in, kind of excites the nucleus enough that it starts to get ready to fission and then kind of skitters off again. And it has a certain particular endpoint energy, and that's the energy that it is, that's the neutron energy coming in. So only some part of its energy gets imparted to the nucleus, but still enough to fission. And then nth chance fission just means that you have a chance to, if the excitation energy is high enough, you could go over the neutron separation energy for the nucleus before it fissions. And then if there's still enough energy left after that first neutron is emitted, then it can still fission, and that can happen several times. And that's why you might see, if you look really closely, some kind of little dips in the neutron number emitted as you go up in energy. And then after the fission, the fragments are de-excited first by emitting neutrons, according to Weisskopf-Ewing distributions. And then when you get to the neutron, less than the neutron separation energy, you can't emit neutrons anymore, and then you emit photons, and that continues until the fragment is no longer excited. So that means you have statistical photons first, and then discrete emission, just like Nathan talked about yesterday. So Freya has 5 basic parameters, which I don't think I'm gonna go into. You can ask me about them later if you want, but I just want to mention briefly something that Nathan discussed yesterday, the neutron angular correlations, which is something that you can only get from a code like Freya. And I'm looking here at neutron-neutron correlations here on the left, and neutron light fragment correlations over here on the right. And the kind of 2-peak structure that Nathan showed yesterday is shown by the black dots. And that's the sum of 3 separate possibilities. The first is that you have each fragment emits 1 photon. And this is because exactly what Nathan described yesterday is you have isotropic emission from each fragment in the rest frame of that fragment. If the fragment is sitting still, the neutron can be emitted in any direction around it. But the fragment isn't sitting still. It's moving away with a couple hundred MeV of kinetic energy between the 2 fragments. And so it's traveling at some very small fraction of the speed of light. And so the neutron gets dragged along with it. That's called kinematic boosting, focusing. So if you have 1 neutron emitted from each fragment, then they're going to be basically moving in opposite directions. And that's what makes this 180-degree peak over here. And if both of them come from the same fragment, you're going to get a peak at 0 degrees. And the light fragment peak will be slightly higher than the heavy fragment peak, just because there's a difference in velocity. And then the same thing you can sort of see over here. If you have a neutron that's emitted from the light fragment, it's following the light fragment. So it's got a peak over here towards 0 degrees. If it's following the heavy fragment, it's moving in the opposite direction of the fragment, of the light fragment, and then the combination of the two is this kind of curve. So these are just some examples of data that have been taken as function of and say this is versus the light fragment, and then these are all neutron correlations over here, and you can see how they changed a bit with the minimum excitation energy. And that's because at some point you're going to have more you're going to get more of a peaky structure, because you're not, I mean, it's going to, the neutrons are moving faster and faster. So it's a stronger peak, stronger focusing, and also affects the neutron, the number of neutrons emitted affects the correlation. So if you have California, which emits like 3.5 neutrons, then, on average, it's not exactly emitting half a neutron, but you're going to get slightly less sharp correlation than between the neutrons, because you can have more than 2 neutrons emitted, whereas over here for plutonium spontaneous fission, where you have closer to 2 neutrons, it's definitely a sharper correlation. So now, angular momentum generation, and this has to do with how fission actually occurs. It's based on nucleon exchange, and so the idea is, this is kind of just a schematic drawing of what I was explaining of how the compound nucleus is formed in the first place. The neutron comes in and it hits a heavy nucleus like uranium-235, and it could hit it anywhere. That's a different, called impact parameter, and where it hits it could affect, it affects how much rotation it can impart to the nucleus. If you hit it in the center, it's going to give you less angular momentum to the compound nucleus than if you hit it sort of on the edge. I mean, that's pretty obvious, just thinking about 2 billiard balls. I mean, but it's more like a ping pong ball hitting a bowling ball. Doesn't give a whole lot of excitation energy, but it gives some. And as it starts to gather that internal energy, then you get rotational energy, and you get statistical excitation of the compound nucleus. Okay, so there are a bunch of papers on Freya and describing what's going on in terms of angular momentum and different observables that you can see here. So Freya, mechanism of fission spin generation is nucleon exchange, and I'm just going. These are some papers that describe the theory of nucleon exchange. Most of them were written by my collaborator, Miriam Randrup. So there are different modes that get excited by the transfer of nucleons between the 2 fragments. I mean, what Kyle was talking about on Tuesday was how you get this neck, and where the neck snaps kind of determines, the something about the way the nuclei rotate. Well, I mean, this is exactly that. That neck is where neutrons and protons can still be moving back and forth between the fragments, and as it gets more and more elongated, the probability of more neutrons or protons passing between the 2 fragments gets less and less. But that movement generates fluctuations, basically, and this has to do with the theory of damped nuclear reactions. And there are these different modes are referred to as wriggling, bending, twisting and tilting, and they have different speeds. And as I was kind of saying already, that these expectations of how the fragment angular momentum develops is based on the nucleon exchange transport model. And then these are the references here again. And I said these transfers back and forth, dissipate the energy because, they move energy from one fragment to the other. But they also have some energy themselves that, kind of acts as a brake on what's happening. And that is going to affect the eventual linear and angular momentum of the two fragments once they separate. And there are different time scales that depend on what's called these mobility coefficients for these wriggling, bending, and twisting modes. The tilting mode is actually 0 for spontaneous fission. And there's a nucleon current. There's the separation between the two centers, which is the radius of each of the two fragments, assuming that they're basically, spherical, even though it's not quite true. And then the distance d between the two edges of the two nuclei. And then the neck radius itself is here. So 2c is the diameter, c is the radius. And it's going to snap when it's a couple of Fermis. So kinematically, you have two moving particles and two rotating spheres. Technically, they should be the same size because we're talking about the same thing. But when you have two moving particles, you can define a total and relative linear momentum, and you can also define a total and relative angular momentum. And then the rotational and kinetic energies are just the sums of these two for each individual fragment, or you can write them as, linearize and write them as in terms of normal modes. And these normal modes are these wriggling and bending and tilting and twisting modes. So before fission, you have something like this. As the neck gets, this neck is still pretty thick, but after, you have two fragments that are kind of moving away from each other as they spin. So you have three coupled angular momentum. You have the spin of each individual fragment, but you also have the orbital angular momentum between them. And that total angular momentum between all three is what's conserved. It's hard enough to measure the spin of an individual fragment. It's like impossible to really get what the orbital angular momentum is, but we know what it is. But there's a fission axis, right? And the question is whether or not your spins are around this axis or parallel to it. So there's been a lot of debate about that, and I'll try to get to that at the very end because it's kind of interesting. I mean, we had this whole workshop last year in Seattle, and one of the things that was talked about a lot was this triangular relationship. Nathan knows all about that. He was there. But anyway, this is S0 for induced fission and 0 for spontaneous fission. And you have these 6 independent internal rotational modes in the wriggling mode. So if the arrow here is along the one direction along the fission axis, then the wriggling modes are going around it like this. Bending, you're going opposite directions, and then tilting, you're going like in the same direction around parallel to the axis, and twisting, you're going anti-parallel. Sorry, but anyway, we put this in Freya in 2014, so it's been in there a while. And now we've just been refining it and, trying to advertise it a bit more in some sense. So I think this is kind of a repeat. It's just showing like which parts of fluctuations are attributable to which modes. And then, so, because we conserve energy and linear and angular momentum, we can explore these different types of scenarios. So and one of the things I didn't mention when I talked about the various parameters was that we have one parameter that basically sets the number of photons Freya will let get emitted from the fragments, and that's what we call some CS. Well, it multiplies the fission temperature, and in this case, we can. What we're doing in some of the studies we've done now is to make that sort of a vector. So CS would be the combination of the different modes, wriggling mode, bending mode, and twisting mode. And I'll explain why we don't look at tilting in a minute, but we have these different probabilities for the mode spins and then different temperatures for each one. And so in regular Freya, default is that the wriggling and bending are fully engaged and there's no twisting. Okay, so I mentioned relaxation times that were based on these mobility coefficients with this that depended on the neck radius, the movement of the protons and neutrons between the two fragments, and the distance between the two fragments. And the wriggling mode is relaxation time is shown here. These are all in femtoseconds, and the neck radius is in Fermis. So, that's really short times. The fission time is thought to be on the order of, say, 1 to 4 Fermis per C. So if the neck radius is in this yellow band here where fission might occur, then the wriggling mode is probably fully agitated because that happens on a shorter time scale than the fission time. And the bending mode is probably fully, close to fully engaged. If the neck radius is really short or the fission time is long, it might not be, and twisting is going to be less engaged than bending. So from that we and we don't show tilting, it's even slower. And in fact, here the tilting is L.R is 0, so it's not engaged. Okay, so you can evaporate neutrons from the rotating fragments. I'm not going to go into any detail here, but we do also conserve the angular momentum of the neutrons. So we find that they don't really, in our calculations, they don't have a whole lot of angular momentum changes the fragment spin. It's the photons that do it all. And so this is sort of similar to the picture that Nathan showed yesterday, except our big fragment here isn't rotating. It's just in this diagram, but it is rotating in real life. So you have statistical photons that just the giant dipole resonance that plus just black body radiation, and then you can emit photons along the ERAS line or join to something called the ripple decay tables, which are just basically transitions between different levels. And all of that comes from nuclear data. So how do we learn about angular momentum based on measurements? a really good question. Some of the work that was done in the University of Michigan group has shed some light on this for sure, especially in terms of neutron and gamma correlations. But as was mentioned already in the previous couple of days, there was a paper by John Wilson and collaborators in Nature, woohoo, of angular momentum generation in nuclear fission. And they said, based on the measurements they made of different individual fragments, they typically did not measure pairs of fragments at all. They just looked at the transitions to various levels. As they looked at peaks in the photon measurements for different decay levels, and from those decay levels, they could identify the nucleus that it came from, even though they didn't actually detect the fragment. And then so they can look at the average spin that they measure, and then this must and then guess what the minimum spin for this other fragment that was unobserved must be. And these slopes are pretty flat, so they say there's no significant correlation between the spins of the fragments. And they interpreted this as that the fragment spins are generated after the nucleus splits. I mean, like this rubber band breaking, I think Kyle mentioned, after they've become two separate independent systems, which doesn't make a lot of sense in terms of conservation of angular momentum. But hey, you can't measure the orbital angular momentum, so who cares, right? No, we care. And you ought to care too, because that's where, that's part of the physics. So you can, I've been talking about these different modes of angular momentum excitation, and the fact is, that sounds like that that should be a really strong correlation, and it is. I mean, if you have wriggling alone, this is very well correlated, and this is also correlated, but in the opposite direction. So it's like throwing a couple of dice. What happened, the correlation is, there's one correlation, that say the one is on the opposite side from the 6, and so on and so forth. So, if you know what the, one dice is showing on top, what it is showing on the bottom, and you can do the same thing for, showing two together. The two are correlated in each throw, but if you take many throws, they're not correlated anymore. And since you have both wriggling and bending that can be excited, they both contribute, and they kind of start to cancel each other out. So you get a distribution in opening angle between the two fragment spins that's very very weak, and you can see that here. And we've calculated it for quite a few different systems here. The correlation coefficient is between 0.1 and 0.2. So, and then this gives an average spin of between like 4 to around 4 for the light fragment, and about 6 or so for the heavy fragment, which is pretty close to what people are talking about having measured. I think I'll skip this part. I mean, they also mentioned, they also did measure the fragment spins by what they, by what they inferred from their photon lines, and they saw that this spin as a function of fragment mass. This is the light fragment over here. Whoops, the heavy fragment over here. So if you squint, you can see, especially here, it looks like similar to the sawtooth, that was mentioned for the neutrons as a emission as a function of fragment mass. And there's some kind of modulation in photon emission as a function of fragment mass, although it's much weaker than that for the neutrons. And say well, you have the same sort of thing for the spin, but it would be nice if you could do a few more, and also measure the fragment. If you could measure the photons and the fragments simultaneously and get their spin, then it would be more convincing, I would say. But this is pretty cool anyway. So we modeled the fragment angular moments of inertia, which are part of the rotational energy, and could see that if we assume that there's some deformation knowledge there, then you get some kind of sawtooth-like behavior as well. I should probably skip a little bit ahead to give you guys time for questions. But so we made a study of these different normal modes, used how we could look at them with the photon measurements. And one thing we noticed is if you're looking at even product nuclei, so that means you have the same, the neutron number and proton number are both even numbers. And that's just because some of these things are easier to measure. And that's actually what John Wilson and collaborators did in their Nature paper. They looked at even nuclei. So the fragment spin could be parallel to the direction of motion, and that's this sideways peaked or oblate shape, or it could be perpendicular to the direction of the motion, which would generate kind of a prolate shape with kind of a back-to-back forward-backward correlation and the cosine of the angle of the photon relative to the direction of the fragment. So we can look at different ways of putting the two, these wriggling, bending, and twisting in, and we can see that standard Freya is typically this oblate shape. If we assume that there is some twisting that's incorporated, then you get something very similar to standard Freya. If you excite all the modes, you get some washing out effect of the two, and it looks pretty flat. If it's twisting only, then you get something that's very close to the prolate shape. So you can look at different different ways of including the twisting temperature reduction, this C twist. And if you go from 0 to 1, this is totally theoretical, of course, but then you can see that you have a steady decrease in what's called the angular anisotropy. And it would be really cool to reproduce this, what's called sort of a classic experiment by Jerry Willamy from the 1970s with more modern equipment and more accurate data. And then you could try to measure the degree of twisting and fission. And you can actually also look at correlation between the two fragment spin directions in terms of their helicities. This is, you see sort of a similar effect that, but I would like to spend the last couple of minutes on this, getting back to this triangular distribution. I think that at least Nathan will find it interesting for sure. I mean, at the Seattle workshop last year, we had 3 different spin opening angle correlations. There was Freya, which was pretty weak. based on our normal modes and the nucleon exchange mechanism. And then we had Bulgak and collaborators' time-dependent density functional theory, and which had very strong correlation that was peaked at pretty high angles. And then you had what's known as asymmetric molecular dynamics, which is peaked around 90 degrees. So how can you understand these huge differences between the results? So we've got the same three coupled angular momentum. This triangular relationship is what I just want to mention here again. So you can make statistical samplings of the coupled spins. I'm not going to go, there's a lot of equations here that I'm not going to go into in detail. But you can sample from each of the normal modes, which is what is being done in this calculation. But I mean, you have a different phase space volume depending on whether you take into account the fission axis or not. It's basically where it's going to go. So if you're looking in 3 dimensions, assuming that everything's independent, okay, then you have, you're not really knowing anything about the fission axis, basically. And you can have independent spins. That's the black dashed line here. You can have touching spheres, which is the red line here, and the dots. And then the decision configuration that we basically more or less assume in Freya, which is that this is about an extra 4 Fermi or so between the 2 radii of the fragments, and this leads to different ratios of the angular momentum. The independent spins assumes that it's 1-to-1 to infinity for where the L0 is the is basically that of the due to L and not the individual spins. Okay, so if you look at the anti-symmetrized molecular dynamics, never mind all the big words there. The point is that it's basically just sampling phase space statistically in all directions. And then what you get is something that's peaked around 90 degrees, but it's similar to decision configuration, but it's also pretty close to the independent spins. And it doesn't look like, so it's reaching equilibrium really fast, basically. Now the time-dependent Hartree-Fock is even stronger correlation than totally random but touching spheres. What they get here is basically corresponding to overlapping fragments, which doesn't really make any sense because the fragments are supposed to be separated when they when they start emitting photons, and the angular momentum is generated. It shouldn't be generated while they're still with practically a compound nucleus. On the other hand, and what Freya does is assume that there is a fission axis. I mean, we just talked about that for like 20 minutes or so. And what we see here is similar to what's in Freya. If you have the regular fission configuration, then you get something very weak, like the green curve here. If they're touching, you get a stronger correlation, and this regular fission configuration is pretty much corresponding to to the Freya scenario. So there may be differences due to the Coulomb trajectory of the fragments, and in fact this is something that's being studied right now. Recoils from the neutron evaporation and from prior photon emission. So I'm just going to leave the conclusions up here, and there's a whole list of references you can look at. I don't have my email on the slides, but it's rlvogt@lbl.gov is the easiest way to reach me. And we can put it in the chat as well. So that's all I have. I know it's a lot, so I'm happy to answer any questions for as long as you like.
All right, thank you very much, Ramona. Yeah, please, if you have a question, add it to the Q&A, and I will let Ramona know and get this rolling. Someone asks, where is your contact? I just put Ramona's email in the chat for everyone to see. So if you click the chat, you should be able to see your email. It is.
So Nathan, after the Seattle meeting, what do you think?
I appreciated the references to the triangles.
Yeah, I mean, just because something is triangular doesn't mean that it has to be shaped like a triangle.
Right. There's a lot of we can't assume anything about this triangle, so we have to assume this thing about this triangle.
Yeah, exactly. It was kind of, and the fact that this thing got published by Bob with the Hartree-Fock stuff, I think is sad, but this goes to show what you can accomplish if you are well known. So nobody has any questions. I'm really sad about that.
Yeah, guys, if you had any questions for Kyle or I earlier this week that we did not answer satisfactorily, now is the time.
Yeah, I am actually a real nuclear physicist. I got my degree in nuclear physics, not nuclear engineering. So, and I had a chuckle when Kyle was writing it. I think like a nuclear physicist. So I know everything went by really fast. But is there anything else I might be able to explain about Freya? Or and you can download it. The latest version is not there. We're still doing some development, but it's published in Computer Physics Communications. Also, I mean, we did have a book chapter and a review, and we just had with Patrick Toulouse, who works on CGMF. We just had a book published by Springer at the beginning of this year, also called Nuclear Fission, with chapters covering the fission cross-section, fission fragments, neutron and photon emission, delayed emission, and applications. And one of the applications is fission in astrophysics that I don't have any slides here for, but it's, and I don't know if anybody saw what I put in the Q&A on Tuesday, but the fission fragment distributions really make a difference to elemental abundances, especially in the R process, especially for the heavier elements. So that's, I mean, you can produce elements up to iron in the cores of stars that then go supernova, but you can't produce anything heavier. The way you produce heavier elements is through the R process, and what called fission recycling means that you kind of build up to very heavy elements, and then they decay by fission, and the fragments move back down on the nuclear chart, and then start picking up neutrons again until they get heavy enough to fission, and then the whole process starts again. So that's called fission recycling, and that can go on for a really long time. And one evidence of the presence of fission would be like MeV, like several MeV photons that would be observed, because they're in late times, because that's the only thing that can cause that high energy, such high energy photon emission.
That's right. Adding to your earlier point, yeah, this code is open source, right? So people can download it and run it on their laptop anywhere in the world, and as long as you have some beginner coding knowledge, you can start to interpret the output. That's really cool.
So there is something in the Q&A about application to nuclear reactors. So reactors are, as Nathan mentioned yesterday, they rely both on the fact that you're not generating a full chain reaction. The idea is to keep criticality basically close to 1. So you have the moderator that slows down the neutrons, and then you have neutron absorbers. So so the delayed neutrons are contributing a lot to the heat that's generated, and keeping the whole thing safe. But a code like Freya, as I mentioned, is really good when you're able to look at small samples. You can use it in a reactor, but I would say, reactor technicians tend to use codes that are based on deterministic models, because there's so many fissions happening at once that it's more of an aggregate system, and the average is not so bad. But I think that one thing to keep in mind is a lot of I also know a little bit about nuclear data, and a lot of the nuclear data that's used in those reaction codes is also really, really old. They don't like some of the newer nuclear data sets available, because it doesn't give the same answer. But it's the new data sets are based on better physics. So there's some kind of tension there. They don't want to change anything that changes the answer, but the physics is still got to be addressed. Does that make any sense? Probably not, but
I think it makes sense. It sounds like there's a lot of momentum with the older data sets, just to keep continuity with a certain model or something like that.
I wouldn't call it momentum. I'd call it inertia.
Inertia, that's better. Yeah.
So, you know, that, so, you know, in reactors, it's, you know, the black box is not so bad, but it may be based on old data too. But it's really amazing how much is still not understood about fission. And I mean, it was first discovered like more than 80 years ago now. And the data that we have is still not very differential. I think this group is doing a great job in doing a lot more differential data in terms of neutron and photon emission. It's not always measured in coincidence with fragments. And you know, if you can measure the fragment and the neutron, you don't. It's complicated to do a really, you know, complete coverage of fission events and fission experiments. And you know, I mean, Nathan could talk about this in more detail in terms of what they've measured at Los Alamos and what they're measuring at Argonne. You know, they use arrays of detectors, but it doesn't cover the whole 360 degrees. There's always going to be some gap, which is where, you know, Freya can be useful because you can help fill in those gaps and know what's missing.
Definitely. And one of the major rubs, I would say, is there's no technology that is well, perfect for measuring both the gammas and neutrons at the same time. So if you have full coverage for one of the emissions, you don't have it for the other. So we rely a lot on informed codes to understand what's going on. There is another question in chat. It reads, is the mechanism of fission explained in textbooks an approximation of what is actually going on, or is it the reality? Probably depends a lot on which textbook you're talking about, that degree.
Yes. I mean, like just the fragment distributions, for example, like what Kyle mentioned. You know, you have mean field theory. You have, so there's some, so you could just do everything like this Hartree, Fock, Bogle-Uboff time dependent density functional theory and all this stuff. So that those things are that's one way of doing it. Trying to do it as this gigantic, you know, many body problem, and trying to approach it kind of in the mean, but still trying to look at the individual fragments. And I mean, I know people who are working on that also in Livermore and Los Alamos, and you know, they get out something that looks approximately right, but it's not exactly right. It's not right by a long shot, but you know, in terms of the neutron observables, it's not, you know, it's not great. It's not awful, but they tend to be too narrow peaks. The microscopic, macroscopic distributions where you produce a potential energy surface and you know, explore that landscape. And so my collaborator also sort of pioneered this random walk approach across a potential energy surface. using Brownian motion, and that does a much better job. But those are just predicting the fragment distributions, and based on with the Brownian, the random walk thing that he did with Peter Muller from Los Alamos, that on potential energy surfaces, that's you have it depends a little bit on where the neck breaks, of course, but that it's great for the fragment distributions, but it's not very good for getting the fragment total kinetic energy right. And people have tried to do this, and it's still not very good. It's still a work in progress. But I would say that I guess our book has probably a fairly complete discussion of the of how the fragments are generated from both approaches. So I would have, if you could look that up, I would definitely suggest it. Or just, yeah, I mean, I'm not trying to sell my book, but we had contributions from people working on both approaches.
There's another question that is asking potentially about a background, I think, for seeing our process vision. So from what I understand, there's plutonium in the debris in orbit from the formation of the Earth and solar system. Correct me if I'm wrong. Do spontaneous fissions provide any help in any research or even any hindrance toward astrophysics?
Well, if there's, so there, plutonium's an interesting case because people first thought they thought that it was only produced artificially in, say, the atomic pile in Chicago for the first time, and that before in the build up to the making of the bomb. Watch Oppenheimer. It's a great movie. It's a really good movie, and it'll give you some impression of how it was. And if you drive to Los Alamos, you'll still see the little house that they have at the gate in the movie. All right. But then plutonium was actually discovered in nature. Maybe even, I don't know if it was at Los Alamos or in Berkeley, but it was by a physicist named Darlene Hoffman, who worked for Glenn Seaborg when she was younger, who was one of the people on the project that discovered plutonium artificially. We're all connected in physics. We really are. But if you produce heavy elements that fission in the cosmos, then probably some are still hanging around somewhere. I wouldn't say they're really in the atmosphere, but they're out in space to some extent. I wouldn't, the abundance is really, really small in any case. You could look up some of these papers I mentioned there and some of the references in there. So spontaneous fission, californium is probably the most used nucleus in measurements of fission, because you get a sample, it sits there and clicks away all the time. There are and until the sample is completely done, it will just you can, some of the plots that I showed of the correlations to way back towards the beginning. Yeah, like this one. So this was done in Russia, but this with californium, this is plutonium-240. Both of these are spontaneous fissioners. Californium has an average neutron multiplicity of about 3.5, 3.6. Plutonium-240 is about 2.1 for the average neutron multiplicity. This paper where this 240 measurement was done also had a californium measurement. The californium measurement was millions of events in less than a day. This took like 2 weeks to get similar statistics for the plutonium sample. I think that's about right. But I mean, you can generate tons of neutrons. And so californium is, everybody measures californium. It's used as the normalization. It's used as a calibration. It's used in lots of things you don't even use for fission at all, because it provides a good neutron source, and it can show that your Monte Carlo background or whatever is working well. Same. So yeah, it's used a lot. Unfortunately, it would be, there's a real dearth of data on even plutonium-239 above thermal neutron induced fission. If you want to look for, I mean, there is no, I'm not sure there's any data like this for plutonium-239 neutron induced fission for thermal, and there certainly isn't anything like it for energies above thermal. So, I mean, spontaneous fission is, ubiquitous for research on fission.
Yeah, they really should be able to do that at Lance, the neutron-neutron angular correlations.
Yeah, but I mean, like with Kainu, yeah, they should be able to do that for different energies, but because they have neutron spectra for all that. So it's probably, they probably have it on tape, but getting somebody to do the analysis, just like one of the first paper we worked on with your group was on photon flash from, so we had photon induced fission of uranium 235, and that was the photons that that came in before the neutrons to induce fission, and they could be separated, and then we looked at neutron correlations from the photon induced fission, and that was something that had never been done before. And even getting P of nu, the neutron multiplicity distribution from that measurement was a brand new thing. So I mean, the data could be there, but there's that whole measurement was so focused on just the prompt fission neutron spectrum, that I don't know that anybody's even thought about trying to get it out.
They did have, they had a paper about, I think it was getting the pre-equilibrium component out as a function of the instant energy, but I don't think they went beyond that.
Yeah, no, that would, that's a simpler thing, because you can also like see that in the spectrum, right? I mean, if you could, like, if you had a really strong pre-equilibrium component at some energy, you would just see kind of a kink in the distribution, because that if there's a single neutron, say 14 MeV that basically bounces off but still causes fission, you would see it, that for one neutron emitted, you'd see like a big pile up at 14 minus neutron separation energy, so around 7 or 8 MeV.
Yeah, and I think they specifically did look at the angular components and found more neutrons in the forward direction for certain parts of the spectrum. But yeah, it's the data definitely is there. Just a matter of who's going to do it.
Yeah, and who's going to pay for it, to be perfectly honest. I mean, everybody wants to know the spectrum for applications. I mean, it's not, I mean, it does contribute to applications, but not the same applications. So it can kind of get lost. I mean, if somebody tried to maybe, I mean, we know people at Los Alamos, we should talk to them about it. And see if we can figure out a way to get it funded.
For sure.
Interesting.
Well, all right. The Q&A has been relatively quiet. I think at this point we'll take the opportunity to say goodbye to Ramona. Thank you very much, Ramona, for delivering this talk. I thought it was really great. And if you have any further questions for her, please write down that email. If you, for whatever reason, cannot manage that, you can always message Kyle or I, and we can put you in contact. So yeah, thanks very much, Ramona. I think with that, we're going to sign it off.
All right. I'll see you later somewhere.
Yeah, see you soon. Bye.
Bye.